In this exercise, we will set up double integrals for the volume of the solid bounded above by the sphere x squared plus y squared plus z squared equals 5, and below by the cone z equals 2 times the square root of x squared plus y squared. On screen, we have the upper bounding surface, which is the upper half of the sphere with radius the square root of 5 and centered at the origin. The lower bounding surface, which is the cone z equals 2 times the square root of x squared plus y squared, can be seen punching through the hemisphere. Since the only bounding surfaces for the solid are the sphere and the cone, following the z direction vertically, line segments start from the cone and go unobstructed continuously all the way to the sphere. Therefore, the volume of the solid can be written as the double integral over the region of integration, which we call R, of f of xy minus g of xy times the element of area dA. If we use Cartesian or rectangular coordinates, then dA is either dx dy or dy dx. But because of the shape of the solid and the bounding surfaces, it might also be worth it to set up the volume double integral using polar coordinates with the variables r and theta. In polar coordinates, the volume can be written as the double integral over the region R of f of x of r theta, y of r theta, minus g of x of r theta, y of r theta. The element of area is r dr d theta. X of r theta and y of r theta simply mean that we replace x and y by what they are in terms of r and theta. We will set up the volume double integral first in Cartesian coordinates. Then we will set up the volume double integral in polar coordinates. First, we use the element of area dx dy so that x will be the first variable of integration. Because the variables of integration are x and y, we have to examine the projection of the solid into the xy plane. To get the projection of the solid into the xy plane, we obtain the intersection curve between the two bounding surfaces. The curve of intersection between the two surfaces represents the farthest extent of the solid in the x and y directions. To find the xy projection of the solid into the xy plane, we take the curve of intersection and translate it straight down into the xy plane. The interior and the boundary of the circular region on the xy plane is the projection of the solid on the xy plane. We must examine the solid's projection on the xy plane to determine the inequalities corresponding to the limits of integration for the element of area dx dy. First, we need the equation of the boundary of the xy projection. Since what we are after is the curve of intersection between the two surfaces, we go back to the equation of the two surfaces. We can use z equals 2 times the square root of x squared plus y squared from the cone and plug it into the equation of the sphere. Z squared on the sphere becomes 4 times x squared plus y squared. This equation simplifies to x squared plus y squared equals 1, and so the boundary of the solid's xy projection is the unit circle. If the element of area is dx dy, then the variable x is the first variable of integration. Therefore, we must follow the x direction on the solid's xy projection and determine from what curve to what curve the xy projection goes. Observe that the xy projection begins on the left half of the circular boundary and ends on the right half. On these two bounding semicircles, and to be more general, on these two bounding curves, we must express x in terms of y, precisely because x is the first variable of integration. On the left half of the circle, x equals minus the square root of 1 minus y squared. On the right half, x equals the square root of 1 minus y squared. These give us the inequalities and the limits of integration for x. Now the variable y is the last variable of integration. This means the limits of integration for y will correspond to the minimum and maximum values of y on the xy projection. The extreme values of y are on the y-intercepts of the circle, and so y is between -1 and 1. And so to write the corresponding double integral for the volume, we start with the outer integral for the last variable of integration. The last variable of integration is the variable y, which goes from -1 to 1. Then we write the inner integral for x, which is the first variable of integration. X goes from minus the square root of 1 minus y squared to the square root of 1 minus y squared. Now for the integrand, or what goes inside the double integrals. F of xy is z for the upper bounding surface. From the equation of the sphere, we solve for z in terms of x and y. And since the upper surface is on the upper half sphere, z is equal to the square root of 5 minus x squared minus y squared. G of xy is z on the cone, which is the lower bounding surface. And so g of xy equals 2 times the square root of x squared plus y squared. We could have taken advantage of the symmetry of the solid and its xy projection, and just have written the integral over a quarter of the xy projection. The viewer can check as an exercise that the volume is also equal to 4 times the integral from 0 to 1, then the integral from 0 to the square root of 1 minus y squared. The integrand stays exactly the same. If we were to reverse the order of integration so that the element of area is dy dx, we can write the volume as the integral from -1 to 1 for what would be this time the last variable of integration, and that would be x. The inner integral, which is now for the variable y, goes from minus the square root of 1 minus x squared to the square root of 1 minus x squared. The integrand stays the same. As a third representation for the volume of the solid, we now use polar coordinates and the element of area r dr d theta. R is now the first variable of integration, and so within the xy projection, or rather this time, the r theta projection, we follow the radial direction starting from the origin and fan outwards to the outer boundary curve of the r theta projection. R equals 0 at the origin and r equals 1 on the unit circle, and so we have the inequalities for r. For the variable theta, since the xy projection or the r theta projection is the entire circular interior of the unit circle, theta goes from 0 to 2 pi. And so to write the volume double integral in polar coordinates, we first write the integral from 0 to 2 pi for theta, the last variable of integration. Then it's the integral that goes from 0 to 1 for the variable r, the first variable of integration. To determine the integrand, we use the conversion equation r squared equals x squared plus y squared. 5 minus x squared minus y squared becomes 5 minus r squared. 2 times the square root of x squared plus y squared would be 2 times the square root of r squared, which technically is 2 times the absolute value of r. But since r goes from 0 to 1 so that r is always non-negative, we can drop the absolute value sign, and 2 times the square root of x squared plus y squared is 2 times r. The viewer can check as an integration exercise either by hand or by using a graphing calculator or a computer software that the volume is equal to 10 pi divided by 3 times the quantity minus 2 plus the square root of 5. Up to 3 significant digits, this is equal to 2.47.